Today's lecture is our first part of 4-7. I split it into two lectures. So we're on 4-7 part 1, which is inverse trig. Wait, I think I called it 4-7a. Inverse trig functions part 1. Yeah. Oh, whoops. Oops. Okay, inverse trig functions part 1. Thankfully, it's pretty easy because we actually kind of already saw inverse trig functions a little bit with those questions that asked you to find two values of theta where sine theta equals something, right? That's kind of the basis of our idea for inverse trig functions, but we do want to define it a little more mathematically in a more precise manner. And so I will begin with the question, does sine x have an inverse function?
Yeah.
Sine x, does it have an inverse function? Who says yes? Does sine have an inverse function? Who says no? If you said no, you would be correct. Sine does not have an inverse function. Why is that? That's because it doesn't pass the horizontal line test. Right? If we graph sine, I'm just going to graph it quickly, obviously. Clearly, it does not pass the horizontal line test because you can literally draw a line anywhere and it will intersect the sine function an infinite amount of times. And so that means that for the sine function, multiple inputs are giving the same output, which means that for its supposed inverse function, that single output would have to map to multiple inputs. And therefore, because that's not possible for a function, the sine function does not have an inverse. For instance, if you were asked, right, if sine theta equals 0, what does theta equal to? Theta could be 0. What else could it be? No. Pi. 2 pi, 3 pi, ad infinitum, right? So there could be an infinite number of thetas that give you sine theta equals 0, which means that there is no inverse function for the sine function. And so in order to define inverse trig functions in a well-defined manner, we actually have to do something called restricting the domain of the sine function. Okay, basically we're restricting the sine function to a certain interval such that the sine function passes the horizontal line test. So you don't really have to know this, but it's called what we call a restricted sine function. So what this means is that if we were to graph our sine function again, right, I'm going to graph 2 periods like a good student. And I'm going to use the method that I showed you guys last time on the video, but not in the lecture because I wasn't thinking about it yet. Okay, so I know that's going to pass through here, 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 here. And so my graph looks like that. Right? And so evidently this sine function does not pass the horizontal line test. But what we can do is restrict it to a certain domain or a certain interval such that it does. And we're going to choose this particular interval as that restricted domain. We'll draw it bigger. We're going to take the sine function, but only between these 2 points. So that's only between negative pi over 2 and pi over 2. Okay, so we're only looking at the sine function between these 2 x values. And now it does pass the horizontal line test, right? Because you can draw a line anywhere through it, and it's only going to intersect once. Which means that this restricted sine function, we can call it sine, but in quotes, this is going to have an inverse function. And so that's how we define an inverse function. Okay? So that means that our inverse function, so we're going to call that inverse sine. And there are two ways of writing it. You can either write it as sine with the kind of -1 exponent looking thing, right? But it's not actually an exponent, right? It's just the inverse function. Sine, or you could say arcsine. Okay, so there are two ways of saying it or writing it. Arcsine or sine with the -1. Make sure you understand that this is not a reciprocal. It does not mean that, okay? Totally different things. Okay? So what's very important is to know the domain and range of the arcsine function. Okay, so what is the domain? What is the domain of our restricted sine function?
-pi/2, pi/2.
Good. And then the range, please?
1, -1.
-1 to 1. All right, and so that means that our new arcsine function is going to just have those flipped around for its range, for its domain and range, right? So that means its domain is going to be -1 to 1, and its range is actually going to be -pi/2, comma pi/2. Okay? Very important to actually memorize the range of the arcsine function, because it can be very tricky. Yeah.
Can you have inverse of cosecant that's limited?
Yep. You have to, every single inverse trig function has to be restricted to a certain range.
Sorry.
Yeah. So let's do cosine next. And then tangent after. And then we're not going to go into arc cosecant or arc secant or arc cotangent. Okay, so let's look at the arc cosine function. Okay, so we're going to graph the cosine function, and then we're going to see where we need to restrict the domain such that it can have a well-defined inverse function. So the graph of the cosine function looks as follows. We all remember that. And this is pi/2, right? That's pi. That's 3pi/2. Here is -pi/2, and here is -pi, and here is -3pi/2. Okay? All right. As you can see, this once again does not pass the horizontal line test. But if we restricted it to the same domain as for the arcsine function, then it would also not pass the horizontal line test, right? It would only get this portion, which still doesn't pass the horizontal line test. So for arc cosine, we actually have to restrict it to this domain, 0 to pi. And that's going to get all of our possible y values, and it will also pass the horizontal line test. So for our new quote-unquote cosine function, its domain is actually going to be 0 to pi, and its range is still -1 to 1. Which means that for the arc cosine function, it's going to have domain of -1 to 1 and range 0, comma pi. Okay, probably should memorize those. Okay, arc cosine domain -1 to 1, range 0 to pi. Any questions? Okay, let's do tangent. I'm not going to draw the graph, but I will tell you the domain for arctangent. Okay, so for arctangent, it's very easy to remember because it's going to have domain that's actually all real numbers, but the range is the same as for arcsine, with a small difference, which is that instead of closed brackets, it's going to be open brackets. And why is that? That's because tangent of pi/2 is
Yes.
undefined, right? And so there is no arctangent function that will give you pi over 2 or negative pi over 2. Okay, so we use open parentheses to denote the range for the arctangent function. Okay, let's do some examples. I want to demonstrate how these restricted domains and restricted ranges come to play. So let's say we had a question asking you to find, what's arcsine of 1/2? Okay? Typically when we encounter these, it's helpful to write it out in terms of the original sine function. So this is actually telling us what is theta such that sine theta equals 1/2, right? That's the meaning of an inverse function, right? Same as with exponents and logs, this is what you did, right? Arcsine is the inverse of sine, and so that means we're looking for a value of theta such that sine theta equals 1/2. And we all did that a ton of times, right? We know this very well. What are the values of theta? Such that sine theta is 1/2? Pi over 6. What else? Good. So there are two possible values of theta, right? But obviously the arcsine can only give us one possible output, and so we actually need to choose one, right? But good news, right? We recall that the range of the arcsine function is negative pi over 2 to pi over 2. And so actually the arcsine function will only give us angle values that are within quadrants 1 and 4, because that's negative pi over 2 to pi over 2, right? So that's maybe an easier way to remember it, that arcsine will only give you outputs in quadrants 1 and 4. And so our answer is going to be pi over 6. Okay? So just remember, arcsine is only going to give you stuff in quadrants 1 and 4, and then you'll be able to solve these pretty easily.
Arcsine specifically?
Specifically arcsine. It's different for arc cosine, which I'll show you right now. Okay? Let's say we had arc cosine 1/2. Okay? In order to find that, we're looking for the value of theta such that cosine theta equals 1/2, right? And again, there are multiple, and we have to choose one for the arc cosine. Okay? So, in order for cosine theta to equal 1/2, we have to be here or here, right? Because we're looking for a point on the unit circle where the x-coordinate is 1/2. So that's going to be pi over 3 and 5 pi over 3 or negative pi over 3. Both work. Okay? But once again, we remember that the cosine or the arc cosine function has a limited range between 0 and pi, right? And so that means only quadrants 1 and 2 will give you acceptable arc cosine outputs. Okay? So the answer is going to be pi over 3. And that's going to be the only output. All right, that's why these restricted domains and restricted ranges are super important, because otherwise you're going to get all kinds of different values for the arc cosine function. Okay? Yeah, Liam?
Would that be a good example of showing your work on a problem?
Yes. Just assume that whatever I write is a good example of showing work. Yeah. Any questions about arc sine, arc cosine? Okay, I'll do an arctangent example. So let's say we're looking for arctangent 1. That means we're looking for values of theta such that tangent of theta is equal to 1. Once again, we've done this a million times. 1? What? So that means theta has to be either pi over 4 or 5 pi over 4. Or 9 pi over 4. Or 13 pi over 4, right? There could be a million different theta values. Well, infinite values, right? But the one we have to choose is specifically in the restricted range that we have for arctangent. And that range is quadrants 1 and 4. once again, same as sine, right? And so only these values on the unit circle are going to be possible, which means that our answer is pi over 4. Yeah,
Will
Liam.
there be no values in quadrant 3 that are,
Arctangent will not give you values in quadrant 3.
well, for all the,
I mean, any arc
terms,
functions.
like any functions, yeah? Like,
Oh, no,
okay.
no, yeah. Okay, so what's really important is really just understanding which domains that are possible, and then you guys should be pretty much set, because we've already done a ton of these, you know, kind of like inverse functions, right? So you guys are very proficient in that now. Okay, so what might be helpful is this little picture that I'm going to draw that really shows you the possible domains, okay? So arcsine can only be in quadrants 1 and 4. So to draw that, that might look something like this. Oops. Okay, so quadrants 1 and 4 only. Our cosine is quadrants 1 and 2 only, right? So that's these two. Then arctangent is only, arctangent is same as sine, right? Except it's a little different because we actually can't include these top points. So I'm going to label those with open circles, right? Because arctangent can never equal negative pi over 2 or positive pi over 2. But it can approach it, right? So that's why I have open circles. Okay, so if you're a visual person, this would be a very helpful diagram to memorize. I mean, you can think about it very intuitively, right? Arcsine is giving you y values, and these two quadrants span all the possible y values. Arc cosine is giving you x values, and so these two quadrants span all the possible x values on the unit circle. And arctangent is a little more arbitrary. Any questions?
There's only all the x values are positive.
No. Arc cosine? It can give you negative values.
Oh, I was thinking in the opposite way here.
Any questions? Well, I'll do a little bit extra. How would we graph the arcsine function? Maybe you guys have had enough of graphing. Just for fun, we'll graph the arcsine function. Anybody remember how we graph inverse functions? They are reflections across
The x, y line.
x equals y line. Inverse functions are reflections of the original function across the line y equals x, right? Which is the diagonal line with slope 1. And so that's exactly what we're going to do. It's basically just, a flip. And so the arcsine function will look like this. It's going to be a reflection of our restricted sine function across that line y equals x. So in other words, we are just going to reflect the line. Where would y equals x be? Y equals x in this diagram kind of looks like this, right? So we're just going to reflect the line across that line. Okay? It doesn't look like slope 1 because the axes are not to scale, right? And that reflection will look like this. We're going to have pi over 2 there, right? And then negative pi over 2 here. Wait, no, that's wrong. Nobody called me out on it. 1 and negative 1. Because that's the domain of our arcsine function, right? And then the range is going to be pi over 2 to negative pi over 2. I'm also going to draw some dotted lines to help me graph it. Okay? The graph is going to look like this. See how that's a reflection of the sine graph across the line y equals x? Well, you have to have a good kind of visual IQ to see that.
Oh, that's low IQ.
No, I'm just saying.
I'm gonna tell that on the fall report.
All right, sounds good.
Little students IQs.
I'm just saying. Just saying. All right, so that's the graph of the arcsine function. Graph of arc cosine. How would that look like, actually? My visual IQ is not high enough to imagine it. Something, yeah. That concludes my lecture.